Perfecto.
Alright. Hi, Mom and Dad. So I forgot to do a recording of while I was giving the talk, so I thought I'd give you guys a rundown now afterwards. So this is going to be my talk. Alright. So today we're going to talk about action recognition in videos. And I read about a method in the paper Scalable Action Recognition with a Subspace Force by O'Hare and Draper. And so pretty much what we're going to try to do is we're going to try to look at a video and apply a label to it. So if we see a person walking, what we want to try to do is label that video walking, similarly with running or jumping. So the basic idea behind this method is three parts. So the first thing we have to do is we have to define a distance between our actions. So normally actions don't come with a distance between them, so like distance between running and walking, you can't just label it with a 4 or 5. So what we need to do is we need to define a distance between actions that makes sense. So we want to say running is closer to walking than maybe running and jumping are. The next thing we need to do is we need to build a decision tree. So a decision tree kind of helps us search through all the actions that we have labeled already and decide what our new action should be labeled as. It helps us not to have to compute the pairwise distances between all of our actions, but rather just a subset of our actions. Alright, and then the third thing we want to do is we want to use an approximate nearest neighbors approach and using a random forest method to classify the actions. So what we do is we have a bunch of decision trees and they all vote on which action would be the best to classify our new action as. Alright, so the first thing we need to do is define a distance. So for some vocabulary, we're going to let T sub I be a tracklet which has 3 dimensions, width, height, and frame. So you can imagine tracklet as kind of a flip book. So we have kind of a stack of papers here, and as we watch the video, we can flip over stacks of papers to watch the video. And on our x-axis we have our width, on our y-axis we have our height, and F is going to be the frame number, so which sheet of paper we're looking at. Working in 3 dimensions is usually pretty hard, so what we want to do is somehow make it into 2 dimensions. And how we do that is we do what's called unfolding, and we unfold it along the kth dimension, so either width, height, or frame. And we label that T sub I superscript K. And so if you have trouble seeing what an unfolding might look like, I have an example in the next slide. But what's important is that now we have this 2-dimensional matrix that we can actually work with. And we use a QR decomposition in order to get a Q matrix, which is an orthogonal basis for our action represented by the tracklet T sub I, and unfold it along the kth dimension. So an example of what unfolding along a frame axis might be is we have this diagonal matrix, and it's of a person doing a jumping jack. So what we have is a block matrix where in the top left corner we have a person starting their jumping jack and then going through the progression as the video goes through the progression. So what we do is we take our stack of papers and we just take the top sheet off and put it in the first place, take the next sheet, put it in the second place, and so on and so forth until we have a diagonal matrix. So that's kind of an idea of what unfolding along a dimension might look like. Alright, so now that we've unfolded our matrix, what we need to do is define a distance between 2 tracklets. So we have our 2 tracklets, T sub I and T sub J, unfolded along the same dimension K, and what we want to do is we want to find the principal angles between the 2 subspaces, QI and QJ, found by doing the QR decomposition. So what we do is we take the cross product of Q sub I and Q sub J.
Sorry.
Q sub I and we take the cross product between Q sub I and Q sub J, and then we use singular value decomposition to get at this matrix D. This matrix D is a diagonal matrix, which means that it only has elements along the diagonal. And then we define our principal angles as the cosine of theta equals this vector, this diagonal vector D, this diagonal vector, which is our singular values. And so then what the researchers wanted to do was use the chordal distance, which is defined as the L2 norm of the sine of those principal angles. And so this is just a number. So once we have our number, this is going to be our distance between our two tracklets, t sub I and t sub j. Alright, and something important to note is that what the researchers are working on is called the Grassmann manifold. And what the Grassmann manifold is a way to map subspaces onto the map subspaces of the rth dimension onto, or the rth dimension in an n-dimensional vector space onto some manifold. And so the reason this is important is because there's no origin in the Grassmann manifold, which means that anything that we just look at by itself wouldn't make sense to compare it to another thing. So if we had just an action running and we assigned it a number, and we had an action jumping and we assigned it a different number, we can't really compare those. All we can do is we can compare the pairwise difference, or the pairwise distance between those two, not the actual singular objects themselves. Alright, so that's important, so we're going to be just working with pairwise distances. So now it's kind of a review of how we build a subspace tree. If we have our orthogonal bases q1 through q6 unfolded along some dimension k, then what we can do is we can take a training sample of these orthogonal bases to build our tree with. So once we have these 4 orthogonal bases, we have to decide how we want to split our node. So if this is our first node, we have to decide when we want to split it. And the 2 factors that contribute most to when we want to split is make sure that there's not too many orthogonal bases in a node, and also to make sure that all these orthogonal bases have a similar action. So if all the bases have a similar action, we want to keep them in the same node. But we also don't want to have a node so big that we have to do a bunch of pairwise distance calculations. So that's kind of the trade-off, and so we're going to explore 2 different ways of deciding to split a node. The first one is called median splitting. So this is pretty simple. Once the number of bases in a node gets above a certain threshold tau, then we decide to split the node. And since we're only working in pairwise distances, what we have to do is select a random pivot node pivot basis within the node, and get all the pairwise distances between the bases and our pivot bases. And then once we have those distances, we can set them on a range, so from 0 to some maximum value, and take the middle of them. All the ones that are closest to the pivot node would go left, and all the ones farthest away from our pivot node would go right. And so that's median splitting, pretty simple. The kind of splitting that the researchers recommend to do is called entropy splitting. And so what entropy splitting is you do the same thing where you select a random pivot basis and you get all pairwise distances. But then after you do that, you map your distances to some partition where you can put those distances in bins. And so for instance, if you have a distance between 1 and 2, or if you have a distance between 1 and 2, then it goes in this bin. If you have a distance between 2 and 3, it goes in this bin, and so on and so forth. And then what we're going to define p sub I as the proportion of the distances in bin I. So for instance, in our graph here, we have a 0.3 proportion in bin 1, so p sub 1 is going to be 0.3. Alright, and then now how we define entropy is the negative summation of p sub I log p sub I. So we note that this is going to be a positive number because we're taking log of a decimal, which gives us a negative number, and we're summing it up and multiplying it by a negative. So it's going to give us a positive number. Another thing to note is that this entropy is going to be maximized when all the distances are in one bin. It's going to be maximized when all the distances are in a uniform in all the bins. So what that means is that you have an equal number of distances in all the bins. The entropy is going to be minimized when you have all the distances in one bin. So that means they're all really close together. And so how you decide to split the node using entropy is doing the same thing. Is once your number of bases in a node gets above a threshold tau, and once your entropy is below a threshold h of t, you split the node. So the reason that we do below a threshold is because if your entropy is low, that means you have a lot of distances and not very many bins. So it makes it easy to split. Say this is really close to my pivot basis. This is really far away from my pivot basis. I'll put the ones that are close to the left and ones that are far away to the right. right? And so after we build our tree, what we can do is actually run and test our random forest. So here's kind of an example of running and testing random forest. So what we have here on the left is a test tracklet. So this is going to be a video of somebody doing like the bunny ears symbol, and we run it through 3 different types of trees. So the first type of tree is going to be one unfolded along the x-axis. The other type of tree is going to be one unfolded along the y-axis, and the third type is going to be one unfolded along the frame axis. So what we do then is once we run it through our tree, we can get a voting system. So at the bottom of the tree is going to be all labeled bases that are similar to our test action, and so we do a voting system. Where we say which ones are closest to our test action, and we take those labels that we already know, and whichever labels have the most votes, that's what we're going to label our test tracklet as. Right. So some perks of using this method is that since we are not doing all pairwise comparisons, we can it's very fast and we can save a lot of computation time. Specifically, we're only going to be doing order of log n pairwise comparisons, where n is the size of our tree. It's also flexible enough to be applied to any set-to-set comparison, so which means that anytime you can get something with an orthogonal basis, you can use this method. And also, the authors claim that this method achieves similar and sometimes superior results to other methods as far as classification. So it's able to get in between 90 and 95% of action classification right. And that is the end of my talk. So I hope you enjoyed it. Sorry you didn't get to see the real thing with everybody asking questions and stuff. But that's kind of an idea of what I've been working on. So thanks. Love you guys. Bye.